Hi, I'm Bob. Welcome back to the solutions to the exercises for the textbook Microeconomics Theory and Applications with Calculus, the 5th edition. We will continue to solve the problems related to sequential dynamic games in Chapter 13 of Game Theory. Here's exercise 3.5. In solved problem 13.2, suppose that Mimi can move first. What are the equilibria and why? Now repeat your analysis if Jeff can move first. We draw a game tree and use the backward induction approach to find the subgame perfect Nash equilibrium. Suppose Mimi moves first. There are two stages in this sequential dynamic game. We first consider Jeff's strategy in the second stage. Given that Mimi supports her son, Jeff gets 2 if he looks for work, but 4 if he loafs. Jeff's best response is to loaf. We underline his payoff 4 and add an arrow on the path. Given that Mimi does not support her son, Jeff's best response is to look for a job because it gives him a higher payoff. We underline his payoff 1 and add an arrow on the path. Next, we figure out Mimi's decision in the first stage, given Jeff's response. If Mimi supports her son, he knows Jeff will choose to loaf, and her payoff is -1. If she does not support her son will look for work, and her payoff is also -1. Mimi is indifferent between her two strategies. We underline her payoffs and add arrows on the path. There are two subgame perfect Nash equilibria. Mimi supports her son. Jeff loafs if his mother supports him, but looks for work if his mother does not support him. Another subgame perfect Nash equilibrium is that Mimi does not support her son. Jeff loafs if his mother supports him, but looks for work if his mother does not support him. The two equilibrium paths are that Mimi first supports her son, and then Jeff loafs. And Mimi first does not support her son, and then Jeff looks for work. In part 2, Jeff moves first. We draw a game tree and use the backward induction approach to find the subgame perfect Nash equilibrium. There are two stages in this sequential dynamic game. We first consider Mimi's strategy in the second stage. Given that Jeff chooses to look for a job, Mimi gets 4 if she supports her son, but -1 if she does not. Mimi's best response is to support her son. We underline her payoff 4 and add an arrow on the path. Given that Jeff chooses to loaf, Mimi's best response is not to support her son because it gives her a higher payoff. We underline her payoff 0 and add an arrow on the path. Next, we figure out Jeff's decision in the first stage, given her mother Mimi's response. If Jeff looks for work, he knows his mother will support him, and his payoff is 2. If Jeff chooses to loaf, his mother will not support him, and his payoff is 0. Jeff is better off looking for a job. We underline his payoff 2 and add an arrow on the path. The subgame perfect Nash equilibrium is that Jeff looks for work. Mimi supports her son if he looks for work, but does not support her son if he chooses to loaf. Recall that a strategy is a plan for different situations. so Mimi's strategy should be stated as above. The equilibrium path is that Jeff first looks for a job, and then his mother, Mimi, supports her son. The outcome of the sequential dynamic game is that Jeff gets 2 and Mimi gets 4. Let's find answers to exercise 3.6. Solve for the Stackelberg Subgame perfect Nash equilibrium for the following game tree. What is the joint profit maximizing outcome? Why is that not the outcome of this game? We draw the game tree and use the backward induction to find the Subgame perfect Nash equilibrium. There are 2 stages of this sequential dynamic game. Form 1 sets its quantity first in the first stage, and then Form 2 sets its output in the second stage. We first consider Form 2's strategy in the second stage. Given that Form 1 sets 180, Form 2 gets 64.8 if it produces 48, 72 if it produces 64, and 64.8 if it produces 96. Form 2's best response is to produce 64. We underline its payoff, 72, and add an arrow on the path. Given that Form 1 sets an output of 240, Form 2's best response is to produce 64 because it gives the highest profit. We underline its profit, 57.6, and add an arrow on the path. Given that Form 1 produces 360, Form 2's best response is to set an output of 48. We underline its profit, 32.4, and add an arrow on the path. Next, we figure out Form 1's decision in the first stage, given Form 2's responses. If Form 1 chooses an output of 180, it knows that Form 2 will produce 64, and it earns a profit of 54. If Form 1 produces 240, it knows Form 2 will produce 64, and its profit is 57.6. If Form 1 sets 360, it knows Form 2 will set 48, and its profit will be 64.8. Form 1 is better off producing 360. We underline its profit and add an arrow on the path. The Subgame perfect Nash equilibrium is Form 1 sets 360, Form 2 sets 64 if Form 1 sets 180, 64 if Form 1 sets 240, and 48 if Form 1 sets 360. Remember that a strategy is a plan that specifies the full set of actions conditional on its rival's actions. So Form 2's strategy should be stated as above. The equilibrium path is that Form 1 first sets 360, and then Form 2 sets 48. The outcome of the game is that Form 1 earns 64.8 and Form 2 gets 32.4. The joint profit maximization occurs when Form 1 produces 180 and Form 2 produces 48. The joint profit would be 129.7. However, it is not an outcome of the game because if Form 1 produces 180 in the first stage, Form 2 has an incentive to switch from 48 to 64 in the second stage to maximize its profit. Let's go to exercise 3.7. A criminal wants the contents of a safe and is threatening the owner, the only person who knows the code, to open the safe. I will kill you if you don't open the safe, and let you live if you do. Should the information holder believe the threat and open the safe? The table shows the value that each person places on the various possible outcomes. Draw the game tree. Who moves first? What is the equilibrium? Does the safe's owner believe the thug's threat? Does the safe's owner open the safe? We draw the game tree and use the backward induction approach to find the subgame perfect Nash equilibrium. The safe's owner moves first. There are two stages in the game. We first consider the thug's strategy in the second stage. Given that the safe's owner opens the safe, the thug gets 2 if he kills the owner, but 4 if he does not kill. His best response is not to kill. We underline his payoff 4 and add an arrow on the pass. Given that the owner does not open the safe, the thug's best response is still not to kill because it gives a higher payoff. We underline his payoff 3 and add an arrow on the pass. We see that the thug's strategy is not to kill, regardless of the safe's owner's decisions. Next, we figure out the safe's owner's decision in the first stage, given the thug's responses. If the owner chooses to open the safe, he knows that the thug will not kill him, and his payoff is 3. If the owner chooses not to open the safe, he knows the thug will not kill him either, and his payoff is 4. The safe's owner is better off not opening the safe. We underline his payoff 4 and add an arrow on the pass. The subgame perfect Nash equilibrium is that the safe's owner does not open the safe. The thug does not kill the owner, no matter what the owner chooses. Remember that a strategy is a plan that specifies the full set of actions conditional on its rival's actions. So we write the thug's strategy in the second stage as above. The equilibrium pass is the pass with 2 arrows. The safe's owner first does not open the safe, and then the thug does not kill him. The owner should not believe the threat because it is not credible. To kill the owner is not rational for the thug because it is not in his interest to do that. In the second stage of the game, the thug's strategy is not to kill, whether the owner opens the safe or not. Thank you so much for watching this video and solving the exercises with me today. See you soon. Take care. Thank you for watching this video and subscribing to my YouTube channel. See you next time.